This is Introduction to Gravity Part 2. It's going to be quite a bit shorter than the first one there. Okay, so this is here talking about the terminal. So we talked about free fall, and we talked about terminal velocity. Look at this. This helps a lot, huh? What does that increase? So, we're talking about terminal velocity and how fast you go. What does that parachute increase? Yes, exactly. It increases the surface area, right? So, that's even kind of a small parachute. I've seen them bigger than that, but, the surface area of this guy would be right there. The surface area of the parachute is a lot bigger. So that is why you reach terminal velocity faster, because you have more surface area to hit more air particles. So the force of the weight, and notice parachutes are pretty light, right? They're not real tough to. You've all played with them in grade school, right? You could carry a parachute around in grade school. But when the force of weight pushing the person downwards is equal to the force of air resistance, then you reach terminal velocity and you float safely to Earth. Okay, so this is really just a lot of review of stuff we've already done. So, except for we haven't really talked about orbiting that much. So orbiting objects are in free fall. So if you guys know about an object, you throw a ball straight, what happens to the path? It starts falling, right? In a curved force, in a curved motion. So here's the idea. If you have this bright blue ball spinning free out in our solar system, that's the Earth, right? If you throw a ball fast enough, then this curved path can match the curve of the Earth. So in other words, for every amount that the ball falls down, the Earth is also curved down that much as well. So it turns out to be something like 7,910 meters every second. The Earth goes down 5 meters. And if you remember your calculations, if to fall 5 meters, it takes 1 second, right? If you start at 0. And since, you're reorienting yourself according to the force of gravity and the radius is the same, it's like you're falling. You're starting from 0 every second. And so then your curve of projectile motion matches the curve of the Earth. And that's all that a satellite does, is it's going fast enough in this way, but not too fast. So when the satellite falls, that curve is the exact same curve as the Earth, the curvature of the Earth. So that's pretty neat. Any questions about that? Okay, so yeah, if you guys want to put something in orbit, all you got to do is get it to go like 7,910 meters per second. Then you're good. Elon Musk does that a lot. He's putting up tons of satellites all over now, right? Okay, so the moon stays in orbit around the Earth because the Earth's gravitational force provides the pull on the moon. So here's the Earth, here's the moon. So the Earth pulls on the moon. Does the moon pull on the Earth? Yeah, the moon pulls on the Earth with the exact same force as the Earth pulls on the moon. So you've heard of tides, right? So when the moon is pulling on the Earth, water moves a little bit better than the ground. So there's 2 places where there's high tides, and it's always over the Earth, over the moon, or wherever the moon is over the Earth, and then on the opposite side of the Earth too. Because the whole Earth moves, and this water, since it's further away from the moon, doesn't have the same force of gravity on it than the Earth does. The Earth is more connected because it's solid, so the Earth actually moves away from the water, and then the water is high tide opposite of the moon, and then the water is pulled more from the surface of the Earth when it's close to the moon. Because the Earth that's on the edge where the water is, like right here, this Earth, is all attached to this Earth. So the whole Earth kind of has to move together where the water is looser. And the Earth can move a little bit separately, but the water is much looser, so that's why it gets attracted to the moon. High tide right next to the moon, and on the opposite side of the moon. Questions about that? Okay. So this is just a description of what we're talking about. Really, the moon is a satellite, and so you can see that the moon is moving this way, but at the same time it's falling down, which is matching the curvature of the Earth. And this is another description of what we were talking about. So this is the velocity at that moment, but because of the force of gravity, there's a y velocity that happens, and then this parabolic path actually ends up becoming spherical when it's orbiting the Earth. They're not all spherical. Most of the orbits are not perfectly circular, but we have to start somewhere, so that's how we start the math. Okay, do you have questions about any of that stuff that we just talked about? Okay. And this is what we've been studying for a long time, is this projectile motion. So we've already been studying it, so now it's kind of just like another explanation of it according to the force of gravity. We just used little g before. But projectile motion is that motion when you throw something off a cliff. It's that curved path. That's a trajectory is showing the projectile motion. And just to reiterate, like we've been studying for a long time, is that this is 2 dimensions. The projectile motion happens in 2 dimensions. One is horizontal and the other is vertical, and we've been doing a lot of work with that. So, and then the last thing is projectile motion has 2 components, horizontal and vertical. We know that. We have the horizontal and the vertical. This is just another expression of that same thing. And like I said, this is really mostly review. But look at this. So these arrows are getting bigger and bigger and bigger. Why are they getting bigger and bigger and bigger? L? Yeah, that's exactly right. Yeah, so the force is pretty much constant. Like in reality, there's, you know, a micro force bigger here because it's a little closer to the Earth. But they call that negligible. But what's actually happening is, you know, the velocity here, it's getting bigger and bigger and bigger as you fall. The velocity is distance per time. And so the distance is getting bigger every second that this thing falls. So that's what that's all about. And that's what makes us have that parabolic path. So to keep going, it'd be getting, eventually it would look like it's falling straight down. And I can imagine, you probably went to the bridge and threw a rock off the bridge, right? And you throw it out and you see they go out, and then all of a sudden it looks like, oh, geez, it's just pretty much going straight down. So that's a good study of projectile motion. Projectile motion has some horizontal motion, and that is constant. Remember, the horizontal is a constant, unless air slows it down, you know, but we study it without air first so we can study the effects of air. Horizontal motion is perpendicular to the Earth's gravitational field. So like if I throw something in that direction, the velocity is in that direction, force of gravity is in that direction, there's no change to that velocity. Because there's no force that's in line with it. Now if I threw a velocity, if I threw like this, then that would mean that this part of the velocity would be unchanged, but this part of the velocity would keep increasing. So part of this is already downwards, which is different than this one. It's fully horizontal. Okay. And that concludes our discussion for this part of the force of gravity. Any questions? Okay. Enjoy your assignment.